Bobby, we have been studying electrical circuits, resistors, Ohm's law, capacitor.
True.
But in high school, when they started teaching us physics, these things in physics, they always talked about something called electromagnetics. I wonder why we are putting together electricity and magnetism. So maybe there is something more we need to learn.
True. Actually, the magnetic field, we don't experience, but it's there always. For example, Earth, there is an Earth magnetic
That
field.
is correct. They talk about a North Pole and South Pole for the Earth. Correct.
Yes.
You are right.
But that is not changing with respect to time. Or it's there, we are not creating.
Correct.
If I want to make my own magnetic field, is there a way?
There must be some way, right? Of course, we know permanent magnets.
Correct.
Right?
Correct.
They have.
Correct.
But
I have seen some old calling bells.
yes.
So when I press a switch, it makes some ting-tong sound.
Correct.
So I read somewhere it has got some coils, and then you are passing current through that. That will become an electromagnet.
That is correct. I've heard that too.
Yes.
So you take a coil. So a coil means, let me guess, it is wire wound around something?
Yeah. So basically, you have several number of turns wound on a former. It could be on a magnetic material or just air. I mean, I can wind it on my finger and form a coil like this. And then if I pass current through that, there will be some magnetic field. That's why this electromagnet formed.
Makes sense.
True.
So let me ask you a question. So last time when you did the capacitor, we built the electric field and so on. This thing will have a magnetic field then?
It will have a magnetic field.
It will have a magnetic
It will have a magnetic field.
And last time you said that if we increase the voltage for the capacitor by some delta V, we will expect some increase in, if you increase the charge by delta Q, you expect an increase in delta V or vice versa.
True.
Right? Will you have some similar effect here?
So here, definitely it is not the charge, but the magnetic field.
Okay.
Maybe it is easy to connect with the Faraday's law.
Yes. Okay.
So you are talking about changing the current.
Correct.
Changing the current will make a change in the magnetic field.
Correct.
So there will be some induced voltage in the
Yes. We know that from Faraday's law.
Correct.
That is correct.
So that induced voltage may be, let's say E is some constant into di by dt.
Okay.
I is the current going through the coil.
Okay.
So it's not. So it is proportional to the di by dt.
Derivative of the current.
Correct.
I see.
Correct.
Okay.
Like in the capacitor, I mean the case here, there is going to be a constant called inductor.
I see.
L.
So L stands for the inductance.
Inductance.
And what are the signs of, we said this induced voltage always has signs.
Yeah.
So we must be following some convention, right?
Yeah. So you may know this Lenzs Law.
Lenzs Law, yes, correct.
So it opposes the very cause that produces.
That is correct.
So it will be minus L di by dt.
Yes.
Okay. So this means if I have an element like this, a coil like this, and if there is a current flow which is time varying, I will know the voltage across it.
Correct. Now, just like that capacitance, we said that the capacitance depends on the geometry of the plates and so on, distance between them, material and so on. So, in this case also L will depend on the number of coils or something like that?
Actually, it may not be that straightforward to explain in theory, that we will do later.
Okay.
But I have experimented this.
Okay.
Let's say if I have more number of turns, then I've seen the value of inductance is more.
I see.
Or if you use, I was mentioning winding on the finger. Instead of that, if I wind on a, let's say, nail, iron nail, then it has got more value.
You know, I have done an experiment. I took a nail, iron nail, I connected it to a permanent magnet.
Okay.
that also started attracting things.
True.
Right? So maybe that has something to do with it, the material of the nail.
Yes. The magnetic property of
property of the nail.
Yes.
I see.
Yes.
Okay. And we also said for the capacitor. Now I am remembering all the things we learned from the capacitor and trying to bring something.
There should be some unit for this.
Yes. Correct.
So I heard something called Henry.
Yes.
So the unit is Henry and the symbol is H.
And for the capacitance, you said farad is very large.
Yes.
And you said it's microfarad and so on.
Similarly, here also mostly you will see in the micro Henry range.
Okay.
And some in millihenry range.
Okay.
And so on.
And similarly, I'm sure if you pick those cell phones, there must be some inductors. They must be in nanohenries or something like that.
Very small inductor.
Very small
so,
inductor.
for example, here you have
I see.
Very
small inductors.
Yeah. So that's in nanohenry.
Nanohenries. Yes. I see. Okay. Maybe here also we will show them. We will experiment.
We will measure and show
them.
them.
We'll measure and show them. We should do that.
Yes. So, like we have the expression for voltage, can we also have expression for current in the
Yes,
inductor?
I think it should be straightforward because we can convert this to integral form.
Okay.
And give them the expression for current.
Okay. So, earlier we were using voltage V. I will use voltage V for convenience.
Yes.
Okay. So, I can just write it as maybe I is equal to 1 by L.
1 by L.
Integral V dt.
Yes.
Okay.
So, depending on which is more convenient, you can use either the differential form or the integral form.
Okay.
Because sometimes you know the current, you want to find out the voltage.
Okay.
Sometimes you know the voltage and want to find out the current. So, it looks like we can do both.
So, this means if there is a constant current going through this.
Yes.
There is no voltage.
There is no voltage. Correct.
So, if I connect it to a 3.3 volt battery.
Yes.
After some time, there will be no voltage.
There will be no voltage, but you should be careful because if there is no voltage, we studied Kirchhoff's voltage law.
Correct.
There needs to be a closed loop where all voltages add to zero.
Yes. So you will be actually short circuiting
the battery. Now that is dangerous because remember the first experiment that you said you took a wire and connected across a battery.
And it was so hot.
It was so hot.
True.
Same thing will happen here. Same thing here. So maybe they shouldn't connect a voltage source across a battery. They can connect a current source.
Okay.
Maybe they can try that experiment.
Okay.
We will do that. Maybe we'll show that in one of the future experiments.
So that is actually kind of indicated from this expression.
Yes, that is correct.
Yeah,
that is correct.
So it's keep integrating. Okay.
Yes.
Can this store energy?
Yes, I'm sure it must be because same way. So the capacitor equation was very similar.
Yeah.
And it was storing energy in the form of electric field.
Yeah.
Here, there is something similar.
So we will try.
Sure.
So, like you mentioned, I can just multiply these two.
Yes.
Get power.
Yes.
Integrate over time. I'll get energy.
Yes.
Okay. Let's try. So energy will be integral
of power dt, which is V
so
times
V
I.
is L di by dt.
L di by dt times I
dt.
times dt.
Okay, so dt will get cancelled.
Correct.
So I have L I di.
Yes.
Okay, which is I square by 2.
Yes.
So okay, so very similar to C, we have half L I square.
Yes.
Okay.
I see. So this energy must be stored in the magnetic
field. Right? While for the capacitor, it is stored in that electric field.
That is right. Very interesting. Very interesting. So looks like a lot of the equations are also similar.
Yes. Yes.
Right, between the capacitor and the inductor.
Yes.
So can we try putting them in series and parallel?
We should check.
We should check.
We should check. Will it behave like a? I mean, let's see.
Let's see.
Because
maybe like a resistor or a capacitor or something else.
Yes.
We will see.
Yes. So I'll try series first.
Let's try series first.
let's say I have L1, L2 and L3 and some current I is flowing.
Yes. And we know from Kirchhoff's current law
Yeah.
that the current flowing through elements in series must be the same.
Same. So the voltage across this will be sum of all this V1.
Yes, and that is from Kirchhoff's voltage law.
Yes. Okay. Let's say V1, V2, V3 are the voltages. So that means I can write V, which is the total voltage across this,
Yes.
is equal to V1, which is L1 di by
di1
dt.
by dt, which is di by dt.
Yes. Okay, so all this di by dt's we can take outside.
Correct.
So basically we have L1 plus L2 plus L3
I see.
by dt,
So it looks
which is very similar to the resistor.
Yes.
At least easy to remember that way. So L equivalent is
L1
L1
plus
plus
L2.
L2.
So looks like if you put inductors in series, they add up to form an equivalent
Correct.
inductance. So if I have had L1, L2, L3 and so on till Ln, I just need to add up all those inductors to get the equivalent inductance.
We'll try parallel.
We should do parallel.
Okay.
I'm guessing it will look like a resistance. Let us see.
Let's
But I'm
see.
guessing it should look like a resistance now when they are connected in parallel.
Okay. So let's say L1. So what is common here is the voltage is same for all. Okay.
Yes.
Currents will be different.
Correct.
So let's say I1, I2, I3, and from the KCL, sum of all this current will be coming from this source.
Correct.
So this will mark it as I.
Yes. And if you had an equivalent inductance,
Ah.
you would have the same voltage and same current.
Correct. L equivalent, and then it will be drawing this current I.
Correct.
So how we will go about?
So shall we write the current in terms of I1 plus I2 plus I3?
Sure, let's try that.
Let us try that.
I is equal to I1 plus I2 plus I3. I1 is L1 di1 by dt.
Correct? No.
No.
We have to use the integral form.
Yes.
So 1
Yes.
over L1.
Yes, capacitor and inductor, I got confused now. So it will be 1 by L1 integral v dt.
Yes.
Okay. So I can take this integral v dt out.
Yes.
Okay. So this is 1 by L equivalent into. Okay. So you are right.
It does look like resistors in
Yes.
parallel.
Yes.
Perfect.
Great.